Hey everyone, welcome to lecture 3, and in this video we will be talking about quick union. In the previous video we talked about quick find, where we had the ability to access the root of any node in order of one time, and in this video we'll be talking about quick union, where it gives us a faster way to union or to connect two or more nodes. Okay, before I begin, let me show you the pseudocode of quick union, and we will quickly go through this, and then we'll try to perform this union operation through this given array, and we'll take a look at how this is different than the previous video of quick find. Okay, so at the start, we'll declare a root array where every node is a root for itself, and this is the union operation, which is pretty much faster. Why? Because in this case, we determine the root of two different nodes, and we change the root of the second node with the root of the first node. Okay, that's it. And the find operation looks like this, where we are doing is we are doing a continuous ascending until we find the root of a node, and we return that node. Continuous ascending is done here in this loop, and we'll keep on ascending until we find that the vertex value is equivalent to the array value. Okay, and once that is done, we will return the root once the vertex and the array value is equal, such as in this case 0 and equals to 0, and we return the root, and that root will be utilized in the union operation to change the root of the second node with the root of the first node. Okay, now let us quickly try to perform the union operations. Let me union 0 and 1. So in this case, let me assume that 0 is the parent for 1. I'll come to this array. Oh, by the way, the kind of array that we're maintaining over here, it is pretty much different than what we maintain in the quick find operation. In the quick find operation, this array was the root array. This array contained the root node values, but in this case, we are containing the parent node values. Okay, and the vertex is again corresponding to the index. Okay, now let me try to union 0 and 1. So I'm assuming that the 0 is the parent for 1. I'll come to the root array and I will change the parent of 0 from 1 to 0. Okay, now I'll union 1 and 2. I come to the array, just give me a second. I've come to the array and I find that the root of 1, it is 0. The root of 1, it is 0. Okay, and the root of 2, currently it is just 2. So what I will do, I will change the root of the second node with the root of the first node. Okay, so what I will do is I will change the root of 2 and I will mark it as 0, and I will say that, hey, in this case 0 is the parent for 2. So the connection will look something like this. Similarly, for 1 and 3, I will change the parent for 3 to 0, and I will make a connection like this. Okay, and similarly for 4 and 5, I will assume that 4 is the parent for 5, and I will join it like this. I'll come to the array, I will change the value of the parent of 5 to be 4, and for 4 and 6, again, for this union operation, I'll come to the array and I will change the value of the 6 to be 4. Okay, now this looks pretty much identical. Why? Because in order to determine the root array, the root value for any node, we see that we are doing that in constant time. For example, hey, what is the root of 2? We come here and we see, hey, the root of 2 is 0. Why? Because we go to 0 and we see that it is 0, right? Hey, what is the root of 3? It is again 0, correct? It seems that we are doing it in constant time, but again, that is not the case. Let me show you why. What if somebody comes and asks us, hey, can you connect 1 and 5? Okay, let us see. The parent of 1 is 0 and the parent of 5 is 4. In that case, what we do? We go to the parent of 5, okay, and we change that to be the parent of the 1. So what is the parent of 5? The parent of 5 is 4. We go to 4, we change the parent value to be the parent of the 1. The parent of 1 is what? The parent of 1 is 0. So we change that value to be 0, and we make a connection like this. And when that is connected, the parent of 5, in this case, it remains 4. The parent of 6, it remains 4. But the overall parent for this component, it becomes 0. Okay. As you can see here, for example, if I try to find the root node for 5, I'll go to the parent, which is 4. The parent asks me go to 0, and 0 tells me he is the root. Okay. Similarly, for 6, it asks me to go to its parent, which is 4. 4 asks me to go to 0. I come to 0 and it tells me, hey, it is the root. Okay. And similarly for 3, which I think we saw earlier, but let me just reiterate it once again. I come to 3 and it asks me, hey, go to 0. I come to 0 and 0 tells me, hey, it is the parent. Okay. It is a root for itself. So the parent, the root for 3 is 0. The root for 5 is 0. The root for 6 is 0. But the root parent for 5 is 4. The parent for 6 is 4. The parent for 4 is 0. But the root for 4 is 0. Okay. And the parent for 4 is also 0. Okay. Yeah. So that's it. So that's it about quick union operation. As far as time complexity is concerned, this thing, it is going to take order of n time because of this loop thing. And this will also take order of n time. Okay? And this will also take order of n time because this is dependent upon the find function, and find function is taking order of n, and this also dependent upon find function, and it also taking order of n. Okay? So more or less, it is taking order of n time. So yeah, that was all about quick union operation. In the next video, we will try to see how we can optimize quick union operation and why do we even need an optimization for quick union operation. Okay, so yeah, I'll see you in the next video then.